Hi everyone. Today we're going to continue with the derivation of free vibration of multiple degree of freedom systems, and we're going to keep on analyzing a 2 degree of freedom like this house that we're modeling as a 2D frame like we discussed in the previous video. So in the previous video we talked about the dynamic equations of equilibrium in the coupled form. So if you saw the first video, which I really recommend you watching, the problem with the coupled form of these dynamic equations of equilibrium was that the motions of the two masses were interfering with each other and we didn't know how to solve it. We also discussed, and very important, how to get the stiffness matrix and the mass matrix for any structure. What we're going to discuss today is a little bit of the expansion of the solution. So we're going to do a little bit of creative mathematics to explore the different solutions, and we're going to introduce the concept of modal circular natural frequencies. And then in the next two videos, we're going to expand on this solution and finalize and wrap up these derivations. So to help you understand these concepts a little bit better, we're going to look into this house and try to use it as an example. For this, let's consider that the mass in the first floor is equal to 5 tons and the mass in the second floor is equal to 3 tons. We're also going to consider that the stiffness of the columns between the supports and the first floor are equal to 3 times 10 to the 4 kilonewton per meter, and the lateral stiffness of the columns or walls between the first floor and the second floor is 2 times 10 to the 4 kilonewtons per meter. So from the previous videos, if you remember how we defined the mass matrix and the stiffness matrix, we can then, in this particular example, write our mass matrix as M1, 0, 0, M2, and in this particular case, M1 is 5 tons, and then 0, 0, and then M2 is 3 tons. In terms of the stiffness matrix, we have K1 plus K2, so that's 3 plus 2, it's 5, and then minus K2, and K2, so minus 2, minus 2, minus 2, and all of this matrix times 10 to the 4. So let's put this example in the fridge for a little bit, and let's look into the mathematics for a little bit. So if we started with the dynamic equation of equilibrium in matrix form, remember that this shape is the shape that has the coupling of the two motions, so that's not what we're trying to do. And we're going to do some tricks to see if we can simplify this equation or make it more useful. The first thing we're going to do is pre-multiply this equation by the inverse of the mass matrix. And in this particular case, the inverse of the mass matrix, or the inverse of any diagonal matrix, is just 1 over the terms of the diagonal. So the idea of pre-multiplying with m minus 1 is that then, when we have the inverse of a matrix times the matrix, this is always the identity matrix. And in a 2 by 2, identity matrix is just 1, 0, 0, 1. So, and for other dimensions, it's just for example, a 3 by 3 would have zeros everywhere except the main diagonal would have 1, 2, 3 ones. The next step is to substitute the vector of accelerations by minus omega squared times the displacements. So similar as we did in the single degree of freedom. So this allows us to substitute this term here by these two terms. The next step is to factorize x, and this leads us to this equation. So minus omega squared times the identity matrix plus mass matrix inverse times stiffness matrix times x. So this in parentheses times x equals to 0. And this is where the things get interesting. If we have two numbers multiplying each other and the multiplication has to be equal to 0, then that means we have two solutions. The first solution is x could be 0. But x could be 0 is quite of a boring solution. It just means that x1 is 0 and x2 is 0. Remember that this x is the vector that defines the displacements of our masses. So to say that x is 0 is not interesting at all, because we're just saying that our system is not vibrating. So even though this is in equilibrium, we're not looking to this solution. So what we're actually looking is to this term, and that's probably the most important equation of today, is this term has to be equal to 0. But since this is a matrix, when we discuss matrices and we want matrices to be 0, we say that the determinant has to be 0. And this equation here is very, very important, and that's what we're going to need to define our oscillation motion. This equation is called the dynamic characteristic equation, and now we're going to learn how to solve for this omega squared. So let's go back to our example, and we have our mass matrix and our stiffness matrix. And again, the inverse of the mass matrix is just 1 over, in this case, 5, and then in the other term, 1 over 3. And then we're going to do the multiplication of m minus 1 times k. If you don't remember how to do multiplication of matrix in a 2 by 2, let's imagine now two 2 by 2s multiplying each other. So we have A, B, C, D times E, F, G, H. So if you want to do this first term of the matrix, let's say the first row, first column term, you do first row of the first matrix times first column of the second matrix. So you do A, E plus B, G. If you want to do this term in position row 1, column 2, you're going to do the first row times the second column. So you're going to do AF plus BH. This term here is on the second row, first column, so you're going to do second row, first column. So CE plus DG, and then the last one is in the second row, second column, so you're going to do the second row times the second column. So CF plus DH. So with this refresher, we can now do the calculation in this case. So 1 over 5 times 5 is 1, plus 0 times minus 2, so we just get 1. Then we get 1 over 5 times minus 2 plus 0 times 2, so we just get minus 2 over 5. Then we're going to go to the second row, so 0 times 5 plus 1/3 times minus 2, and we get minus 2/3. And then the last one, so second row, second column, 0 minus 2 is 0, and then 1/3 times 2 gives me 2/3. And here we're just going to multiply everything by 10 to the 4, and now we can see the magnitude of this matrix straight away. So now we figured out how to get this ingredient of the equation. So m minus 1k is just equal to this matrix. And now we need to do m minus 1k minus omega squared times I. So omega squared times I, and remember I is just 1001, just gives you this little matrix here. So minus omega squared 0 omega squared, and then there's the minus applies to the entire matrix. And before we continue with the calculation, just to simplify it a bit, we're going to call this omega squared lambda, because this allows us to write the equations a little bit faster in the next page. But it's the same thing. So omega squared and lambda in this case have the same meaning. So with this substitution, we can now say that m minus 1k minus lambda I is just this matrix, so with the minus lambda in the main diagonal. And if we want to solve for a determinant, and again, if you don't remember how to solve for the determinant of a 2×2, is nothing more than the main diagonal, so AD, minus the other diagonal, so AD minus BC. So if we want to apply it to this matrix, and again, we have to make sure this is equal to 0, we're just going to do 1000 minus lambda times 6666 minus lambda, and then minus 4000 times minus 666.7. So again, this diagonal minus this diagonal. And if we want the determinant to be equal to 0, this has to be equal to 0. So the next step is just expanding the brackets, and please feel free to stop the video to do this in your calculator to make sure everything is okay. But the idea is that eventually we're going to get to a quadratic equation, and we're going to use the quadratic formula to solve for this equation. And again, see that the solution to this equation is lambda. And remember that lambda is omega squared. So we're solving this orange equation for omega squared. And that's important that you understand this at this stage. So if you solve the quadratic equation, you get two solutions. One is around 2,900, and then the other one around 13,760. So if these lambdas are equal to omega squared, we can resubstitute, and then we can use the square root to find omega 1 and omega 2. In this case, they will be 53.9 radians per second and 117.3 radians per second. So now we wasted all this time solving for this secret lambda, and it's no coincidence that we use the letter lambda in this case. We know that lambda has a physical meaning for dynamics of structures. We know that it's called the circular natural frequency. But these specific ones have an extra meaning to it. These are called the modal circular natural frequencies, and they are the key to solve the coupled equations that we mentioned in the first video. For now, just know that mode 1 is described by the smaller value of these two. So in this case, we had a 53.9 and 117.3. Mode 1 is always defined by the smallest of the two, okay? So in this case, the circular natural frequency of mode 1 is 53.9 radians per second. And the circular natural frequency for mode 2 will be the second smallest value, so 117.3. If we have more modal circular natural frequencies, the third smallest will be mode 3, and the fourth smallest will be mode 4. But because we're only solving a 2 degree of freedom system, by definition, we only have 2 modal circular natural frequencies. But know again that this applies to any structure in the world. So if we have more degrees of freedom, we would have more modes, and you always need to take them in a ascending order. So the smallest mode 1, second smallest mode 2, and so on and so on. So in summary for today, The only thing we learned how to solve was we took the mass matrix and the stiffness matrix, and we learned this dynamic characteristic equation. The determinant of the inverse of mass matrix times stiffness minus omega square I has to be equal to 0. And if we take this equation and we solve for omega, we're going to get omega n, so the modal circular natural frequencies for any mode that we're considering in our structure. Thank you for watching the video. Definitely watch the next one that we're going to discuss about mode shapes, and that will make a little bit more sense on what we're talking about. But for now, thank you for watching and have a good day.